Video about section 6.3, normal distributions. We had previously gone over why we're learning about normal distributions and how they're extremely important to science and math and business and everything. I mean, normal distributions are extremely important in all fields these days. But yeah, so I don't think for one of the classes, maybe A block, we didn't go over this part of it. And so just realize that we can't just call something a normal curve because it looks like this. It has to meet specific criteria, and some of the specific criteria is that it needs to follow the 68, 95, 99.7 rule, which means that 68% of the data needs to be between 1 and 2 standard deviations of the mean. And let me use a different color. Let's say, let's go here. Let's say 95% of the data needs to be between 2 standard deviations above and 2 standard deviations below the mean. And then a different color here. Let me try and do something else. Let's go blue. And 97% of the data in a distribution has to be between 3 standard deviations below and 3 standard deviations above the mean. So as I'm saying this, I realize that you probably don't know what standard deviation means, and that was defined up here. So right up here, they defined for you what mean and standard deviation is. So mean we're calling x bar. Sometimes this is called mu. In AP statistics for normal distributions, we call it mu, but which is the Greek letter M. But here we're just referring it to as it is x bar, and so that means mean. So the middle of the distribution, or the mean that you traditionally learned, which is add up a bunch of numbers and divide by how many numbers there are. So what you think of mean is what x bar means, okay? And then standard deviation, we denote it this way, called sigma. We call it sigma, so you make like a little circle with a squiggly line at the end, sigma, and that basically just tells you on average, okay, standard deviation is the average distance of values in a data set from the mean. Okay, so if I see how far all these values in this distribution lie from the mean, and I calculate basically the average distance that all of them are away from the middle or from the mean, we call that distance standard deviation. There's a complicated formula for that, and maybe this is a complicated definition for you, but the purpose of this class is not really to focus too much on the definition of standard deviation and how it's calculated, all that kind of stuff. Just basically understand that a normal distribution, any normal distribution, has to meet these criteria, so that 68% of the data lies within 1 standard deviation of the mean. Within means here's the mean plus 1 standard deviation, or the mean minus 1 standard deviation. So 68% of the data, like we said earlier, should be here. Okay, that's one way of looking at this. What they've done for you here in this textbook, we don't actually do this in AP Statistics, but what they've done in this textbook is they've also broken that down into smaller subdivisions for you to be able to do finer calculations. And I think maybe for most students, so you should be aware of this rule right here, but I think for most students, maybe this is more useful to answer the types of questions that the textbook asks you. And they will go into what you actually do on a calculator for real-world problems. But for these initial type of questions, something like this may be more useful. So what this says is between, that's not a very straight line. This says between the mean, which is x bar over here, okay, and 1 standard deviation above the mean, which is this, this slice has 34% of the data of the distribution. And notice, please, these are called density curves, and underneath the curve there's 100% data, okay? And so your calculations can add up to at most 100% of the distribution, all right? But then it says, if I go to the left, one standard deviation below from the X bar. Then if I do this, I get another 34%. Now you'll see, wait, that's the same as what we said here. One standard deviation below, one standard deviation above, that's 68%. Well, here they've just chopped it in half. Okay, so these things are the same, but I think for most students, using the little distribution on the right here, this one, it's easier to do calculations. Okay, so let me stop talking about it. I think what you'd have to do is probably memorize this graph right here. If I were you, I would get that in my head. And then I'll show you how to use it. Okay, so here's a question. A normal distribution has means x bar and standard deviation sigma for a randomly selected value. So remember, we were all about random variables. So our previous section 6.2 were about random binomial variables or random variables, but those were discrete, different kinds of things. And don't worry too much about what discrete means, but these are still random variables. It means x here, the small x. If I randomly pick a number from this distribution, I just randomly go here and pick a number, okay? And that's a number. X equals, who knows? Let's say it's 5 or something like that, okay? This is saying whatever that number is, without knowing its exact value, whatever that x value is, what is the probability? So this p means probability that the number is between one standard deviation below the mean and 3 standard deviations above the mean. So 1 standard deviation below the mean is here, and 3 standard deviations above the mean is here. So what I teach students to do is draw your own picture. Okay, you can't use this picture because it's not going to be there on a test or in your homework. So you have to basically draw your own picture. So let's draw our own picture. Just very, very rapidly draw a little rough sketch. Ooh, that's ugly, but that's okay. And then we're going to say the mean is here. And we're going to say the mean minus 1 standard deviation, which is the lower bound here, is there. And so we're going to do this. And then say the mean plus 3 standard deviations. So that would be here. Okay, is there. And then the question is, what is the probability that if I randomly pick an x value from the distribution that it comes from here? So you can choose to shade that. I think that's a good idea. Shade this in. And then now you know what you're looking for. So, but basically you're breaking this into chunks and saying what size is each chunk. Okay, and then you can calculate the probability. So you should get used to writing probability like this. Probability that x, a randomly selected x there, is between x bar minus sigma and x bar plus 3 sigma. Okay, and don't worry too much about how attractively you are writing sigma. It takes some practice. I still mess it up all the time. And that's equal to, and then you calculate the probability. Now probability is actually a decimal number, but here they're using percentages, so I'll accept either answer, percentages or decimal numbers, but it's actually a decimal number. But so according to this chart, 34% is here. This is 34%. This little chunk right here, according to the chart, is 13.5% of the distribution. And then this last little chunk here is 2.35% of the distribution. So that's what you have to do. You take all that and just add it up. So you get 34% plus 34% plus 13.5% plus 2.35%. And if you add that all up, you get 83.85%. Okay, so this is, or like I said, if you want to do decimals, which is technically better, this is the probability. Okay, probability is a number between 0 and 1. Percentages between 0 and 100. Okay, similar idea. All right. So there's the probability. So yeah, I won't do all of this. I think you can do most of these by yourself. We did one where x is between two values. Let's do maybe a less than and a greater than, and we'll stop there. And you can look at the completed note sheet if you want to see more. So let's do another quick example. Again, please draw a graph when you do this in your homework, especially as you're just getting used to normal distribution shape and properties. So this question is saying, what's the probability that I randomly select an x value? I randomly go here and pick an x value. Okay, that's what that says. And that it is less than x bar minus 3 sigma. Okay, so here's the mean x bar. And then if I go 1, 2, 3 this way, 3 standard deviations. So here's x bar minus 3 sigma. So the question is, what's the probability that x is less than that? Okay, so less than that would be out this way. All right, and if we refer back to this given diagram here, less than would be this way. So here's 3 x bar minus 3 sigma. Less than is this little sliver right here, which we just drew, and that's 0.15%. Now just be careful. If you write this is 0.15%, that's fine. If you want to write this as a decimal, it's 0.0015. Just be careful with your conversions if you want to use decimals instead of percentages. Okay, and then for this question here, similar idea, rough little sketch here. The picture quality is not that important. X bar, and then what's the probability that a randomly selected x value is greater than x bar plus 1 sigma, or 1 standard deviation. So x bar plus sigma. Okay, so the question is 1, 2, 3. This goes all the way to x bar plus 3 sigma. And then basically there's very little data out there. And so the question is, what's the chance that if I randomly pick a value from here, that it's here or bigger, which means all of this included. Okay, and so your answer consists of those 3 slices from the distribution. Okay, so again up here, there's x bar plus sigma, and it's these 3 pieces of information here that make up your solution. So basically you're saying the first little sliver is 13.5%. This little piece here is 2.35%, and this little piece here is 0.15%. Okay, and so it's that plus this plus this. Okay, that makes the answer. And if you do that, you get 16% about, which is basically 0.16. Right? And then this letter C is another example like this one up here. So I'm not going to go over that one with you. All right, you can look at the completed note sheet for that. All right, so let's move on to actually putting this in context now, and then hopefully we can get through this as fast as possible. I'll show you some calculator things you can do here to solve these types of questions. Okay, so if we do this, let's do another example. It says the blood cholesterol readings for a group of women are normally distributed. That means we know that it works this way and it works this way. Okay, that's what they're telling us by giving us that information. All right, saying it's normally distributed, that's what it means. All right, and then with a mean of 172 and a standard deviation of this. So they're telling you x bar is this, and they're telling you sigma is this. Okay, 14 milligrams per deciliter. That's what they're telling you. Okay, and so then the question is about what percent of women have readings between these 2 numbers. Well, what you have to do here is actually draw the distribution, draw the picture that really tells you what you're looking for. So if you just draw what they're talking about, what percent of people will have readings between these 2? Well, let's draw the normal distribution. Let's just draw the normal distribution, and then we can worry about answering the question. And so what I have here is the mean. So we said mean is x bar, but in this case that's 172. All right, and then 1, 2, 3 standard deviations above the mean, and 1, 2, 3 standard deviations below the mean. So if I go mean plus 1 standard deviation, this would be 172 plus 14. That's x bar plus sigma. And if you do the math there, you get 186. Okay, so what I have here is 186. And then if you just go another standard deviation to the right, you're saying this is the mean plus sigma. Well, this would be the mean plus 2 sigma. So I'm just going to do this once more. That would be 117.2 plus 14 plus another 14 for the 2 sigma. And then for that you get 200. Okay, 200 would be your 200 milligrams per deciliter. So 200. And then if you add another 14, you get 214. They made this nice and easy to do the math for. Okay, and then if you go standard deviations below the mean, that means here you're saying x bar minus sigma, so you're doing 172 minus 14, and that would give me 158. Okay, so now we're talking about 158 here, and if you keep going, 144 and 130. I'm not going to require that you always draw all the information on here, but it's definitely helpful initially for you to figure out what's going on, okay? To draw as many standard deviations on your picture. Now let's answer the question. If I were to randomly pick a person from this distribution, what's the chance, or what percent, what's the chance they'll be between 158 and 186? Now that's an easy answer. You know the answer. The answer is simply 34 plus 34. Okay, 34 plus 34. So you would go, now please, you can write this properly. The probability that a randomly selected person is between 158 and 186 would be 34% plus 34%, which is 68%, or 0.68. Okay? That's one way you can do that. And then this would be a similar question. So maybe I should do example 3. Let me do letter B, and then I'll stop there, and then we can... I'll let you try example 4 on your own. That's not really any different. Similar type of question. Yeah, so let's do letter B, and then we will move on to the standard normal distribution. So letter B says readings less than 158 are considered desirable, but what percent of readings are desirable? Okay, so some wording there. So here's my distribution. And I guess if you've just drawn the distribution, don't feel obliged to just draw the whole thing again. We already did it over here. And so less than 158. So this is the question. What is the probability that if I'm a randomly selected woman, that X, that my reading is less than 158, right? And that's 158 milligrams per deciliter. So what is that probability? So we go to 158 and we say this is the area of the distribution. Those are all the people that meet that criteria. So if you want to use the thinking from the previous page, let me erase some of this stuff. If you want to use this thinking, then we're doing 158 would be one standard deviation below. So we're saying it's these chunks right here, 13.5, 2.35, 0.15. Okay, so this would be 13.5. This would be 2.35, and this would be 0.15, and these are all percentages, okay, percents. So you'd say, oh, this answer would be 13.5% plus 2.35% plus 0.15%. And if you add that all up, you get, oh, interesting, again, 16%. Numbers will come up often because it's the same chunks we're adding up, okay? So that's letter B. That's basically how you use either of these two diagrams to answer probability questions about the normal distribution. Okay, a regular normal distribution, and this was more, example 3 was more in context. All right, so let's talk about standard normal distribution. So this is a big topic, and actually I'm going to teach you this quite differently from the way that the textbook does or that I've done in the past, because we have technology called a calculator, right, that really helps us do things properly. So the standard normal distribution is a very powerful tool that we have, and it's important that you understand what this means, what this is all talking about. So standard normal distribution is still a normal distribution, but For the standard normal distribution, the mean of the distribution, x bar, is always 0, and sigma, the standard deviation, is always 1. And so if you look at this, it says z equals 0. What does z mean? Okay, what is z? What are we talking about? Z is a z-score, okay, and that's, instead of writing here x bar and x bar plus sigma, which technically those would be the same thing. X bar is 0, and x bar plus sigma is 0 plus 1, which would be 1. That is true, but we don't write that really for the standard normal distribution. We just call it a z-score. Okay, we call it a z-score, and a z-score comes from taking a specific x value, subtracting the mean of that distribution, and dividing by the standard deviation of that distribution. And we call that process standardizing. Okay, doing this to values from a distribution is called standardizing. So we could go back to our previous distribution here and say, let's find a z-score for this. And you would say z is equals to, this is the particular x value I was interested in looking at, and I know that the mean for this distribution was 172, and I know that the standard deviation was 14, and I can turn this into a z-score. Okay, you can do that for any distribution that's normal. You can standardize it and then get the standard normal distribution and figure out where this would be relatively to the mean and standard deviation of the standard normal distribution. So the most powerful thing you have to understand about this is the standard normal distribution does this. Okay, we have this powerful formula called z equals x minus x bar over sigma. And what happens is this. I take one normal distribution that, let's say, has mean 172 and standard deviation 14, which gives me things like this. Okay, and if I take all the x values from this distribution and I run them through this formula, what pops out is this distribution. And you go, okay, why would I want to do that? That seems great, but why do I need to do that? Okay, and the answer is, well, I can also take, let's say, another distribution with mean 200 and standard deviation 20. Okay, mean 200 and standard deviation 20, which is clearly not similar to this one. They are both similar shape and they have some similar properties, but they're not the same. Okay, for me to make a comparison between these two distributions would be quite tricky. But what the standard normal distribution allows me to do is I can also standardize all these values, and then what pops out again is the exact same distribution. Okay, so I can take any normal distribution, standardize it, and come up with the standard normal distribution, which is really, really powerful. So then I can make direct comparisons between two distributions that are seemingly very different, because I can place x values somewhere on this distribution here. Whether they come from the red or the blue distribution, I can still make comparisons. Okay, and the other thing that's very useful about this is someone has figured out exactly what the area is underneath this distribution right here. So this distribution, we know exactly what the areas are under here. And when I say exactly, not like estimations like this. These are rough estimations. They're not really very accurate. So when you take calculus, you'll learn, one of the big parts of calculus BC is integration, which is finding area under curves. Okay, and so mathematicians have integrated the nonsense out of this curve and given us all the values for small little intervals. So if I want to know from here to here, or from, small little intervals, what's the chance that I pick a value between those two intervals, we can figure it out with the help of calculus. Now, you don't have to know calculus. Our calculator has this information in it, so we can look stuff up. Okay. What we used to do is to teach you to use a table, and it's called the standard normal table. Right here, standard normal table, to calculate probabilities from a normal distribution, things like that. But that's really not necessary anymore. So I spoke to the other teachers about this lesson and said, in AP statistics, we don't even really teach this anymore because we're fortunate and blessed to have calculators who can do the stuff for us and give us actually better answers even than the table can. So I would say please don't worry about this part of your note sheet. I'm going to show you how to do all this on your calculator. It's much faster, much better, and easier to understand. Okay, so let's not worry about this. I'll show you how to calculate a normal probability on your calculator. All right, so let's do an example. Let's get out of here and finish this lesson. All right, let's do an example. So it says scientists conducted aerial surveys of a seal sanctuary and recorded the number X of seals they observed during each survey. The numbers of seals observed were normally distributed with mean 73 and standard deviation 14.1. All right, so that's great. So my X bar is 73 and my sigma is 14.1. And then it says find the probability that at most 50 seals were observed during the survey. Okay, so actually because of our calculator, we don't actually have to do all the work that the textbook wants you to do. We don't have to standardize. We really don't have to do this to answer the question. But I'm going to take you through the process in any case because it's really important that you understand that we can standardize normal distributions for comparison purposes. Okay, so I'm going to go through this in any case and show you this the proper full explanation here. Okay, so it says find the probability that at most 50 seals were observed during a survey. So here is the question that you would write if this was, let's say, our first or second example here. What's the probability that I fly over this seal sanctuary and I observe at most 50 seals? So at most 50 means less than or equal to 50. First of all, remember at most means less than or equal. Okay, and so we say, okay, so on a random day, I fly over and I count seals. That's X. What's the probability that that X value is less than or equals to 50? All right, but now we're saying, hey, we can standardize this and turn it into a distribution that looks like this that we know everything about and we can find the probability for. All right. So we're going to do that. Let's say what's the probability and we're going to standardize. So we're going to use this little formula inside our probability statement. Okay, see if you can track with me here. So we're going to say what's the probability that Z, my Z score, so I'm going to standardize, is less than or equal to, and then I'm going to use my standardized formula, okay, my Z-score formula, which is, we know it's this, Z equals X minus X bar over sigma. So what we're going to do is fill that formula in, and we're going to say X is 50, this is my X value, okay, and we're saying minus the mean, which is 73, over sigma, which is 14.1. So what we're going to write is the probability that X is less than or equal to 50. That's the same as the probability that Z is less than or equal to the standardized value, 50 minus 73 over 14.1. And if you punch that in your calculator, you get this. That's the same as the probability that Z is less than or equal to negative 1.63. Okay. Now, question is, how do I come up with this answer? If you go back and look at your diagram and stuff you've memorized for areas and things, we didn't memorize anything like this. What, negative 1.63, what? I don't know how that works. So the beautiful thing is that your calculator can do this, okay? And so we're saying, what's the chance that Z is less than negative 1.63? And because we've done this process of standardizing, we're now talking about the standard normal distribution. So we've taken a distribution with mean 73 and 14.1, and we've converted that to a normal distribution, a standard normal distribution. So let me just illustrate that for you. Here was our original distribution, and if I add 14.1 to that, what do I get? 87.1 or something like that. So here is my original distribution. We standardized it. Ooh, I should change that arrow. We standardized it. If we run every value through that formula, Then we come up with a new distribution. It looks like this. Mean is 0 and standard deviation is 1. Okay, and we know everything about it. So we're going to just go and do the probability calculation from here on our calculator with a distribution with mean 0 and standard deviation 1. So if I go to my calculator, you just do this. You say second and distribution. Okay, and then we go to normal CDF, normal cumulative density function. Okay, and we're going to say lower bound. So if I go back here, say what is the lower bound? What is all the way on the left of negative 1.63? So if I were to draw this picture like we did before, negative 1.63, here's negative 1, here's negative 2. Negative 1.63 would be here. And we're asking what's less than or equal to that. So it would be everything out here. Okay, we're asking what is the area there, which is equal to our probability. Okay, so the lower bound, what we teach students to do is to say lower bound, just you can either leave it like this, which is a very small number, or we just say negative 10,000. Okay, that's basically 0 in terms of the standard normal distribution. And then the upper bound is what we're asking for here. So I'm going lower bound all the way from the left here up to here. That's my upper bound. Okay, so my upper bound is negative 1.63. And then we're going to say mean is 0, standard deviation is 1. Yes, we standardized, so my mean is 0, my standard deviation is 1. And so we can just go down there and enter on paste, and you get this number. Okay. So if you use the table, you would get a very, very similar answer, but 0.05, and we usually round to the third non-zero decimal. So if I round this to the third non-zero decimal, that's 515. I have to round here, so that's 516. So you get 0.0516. That's the answer. Okay, that's the answer. Now we've done all the work here, so we can just answer letter B. Okay, letter B, and then we'll just jump right into example 6. So hopefully that makes sense to you. Again, and I'll show you the commands in your calculator again. So here's another question. Find the probability that at least 80 seals were observed. So at least means greater or equal. Okay, so this is the question. From the original distribution, what's the probability that x is greater or equal to 80? And we can go again and say, let's standardize that. What's the probability that z is greater or equal to? And take 80 minus the mean that they gave me at the top here. Okay, 80 minus 73 over the standard deviation they gave me at the top here, 14.1. And then we get this, which is the probability that z is greater or equal to. And you put in there 0.49. Okay, if you calculate that, you get 0.49. All right. Now, the nice thing about this is your calculator can do this calculation too. Okay. Man, I'm not sure what's happening here with my tablet. It's just not maintaining a connection today. Let's see. Wow. I'm sorry, guys. I'm not sure what's happening here. This is taking an interesting turn. All right. So there's that. Sorry, I had to reconnect my tablet. So, what's the probability that z is greater or equals to 0.49? So we go back to our calculator and we do this. Second distribution, normal CDF is the one you want, number 2. And we go lower bound. Now, if we look at our distribution, now we're asking a different question. We're saying z is now 0.49, which is almost halfway here. And we're saying what's the probability that z is this big or bigger at least, right? So now we've got a different question. Now my lower bound is now 0.49. Okay. Look at the graph again. This is my lower bound now, right here. And then my upper bound should be infinity, but we can put 10,000 because that's a very, very big number in terms of standard normal distribution, standard deviations. Okay. And so if we do this, we get 0.312. If you round to the thousandth or the third non-zero decimal, you get 0.312. 0.312. All right? So there's that. And then let's do one last example and we'll be done. Okay, and here's the last example. It says a survey of 20 colleges found that the average credit card debt for seniors was $3,450. That's a lot. The debt was normally distributed with standard deviation so much. Okay, so average. So what they're telling us here, average X bar. They're telling you X bar is 3,450. And then they're telling you that standard deviation, sigma, is 1175. That's what they're saying here. Okay. Now they're asking a bit of a different question. Find the probability the credit card debt was of a randomly selected senior was between these two numbers. All right. So what we're going to do is standardize and answer the question based on the standard normal distribution. You could do it directly, especially since you have a powerful calculator, but I'm going to show you how to do this by standardizing. So here's the question. They're asking, what's the probability that a randomly selected X there, X is the randomly selected senior, okay, that their debt is between these two numbers, $3,600 and $4,000. That's the question. And what we're going to do is standardize both of those numbers at the same time. So we do this and we say 3,600 minus the mean that they gave us. The mean they gave us is 3,450. So 3,450 over 1175 was the standard deviation. And once I standardize, this turns into a z-score, okay? And that is less than 4,000 minus the same calculation. 3,450 over 1175. Okay? And when you do that calculation, you get this. What's the probability that z is between these two numbers, 0.13 and 0.47, if you just simplify that calculation. And now your calculator can do this very, very easily too. No problem. All you do is you go back here and you say second distribution, normal CDF, enter that, and my lower bound now, let's draw a picture here again to show you what we're actually doing. Here's my standard normal distribution, mean 0, standard deviation 1, and so on, okay. I'm not going to draw this very accurately, I just want to show you basically what we're doing. And then 0.13 would be about here, well, maybe even closer. 0.13 would be really close to this, okay? And then 0.47 would be over here, 0.47, maybe closer to, maybe a little bit less than half. Well, in any case, you get the idea. This is what we're looking for, this area, okay, on the standard normal distribution. So my lower bound is now here, and my upper bound is now here. So my lower bound is 0.13, okay, is 0.13, and my upper bound would be 0.47, okay, and still mean 0, standard deviation 1, because we standardized these values to be on the standard normal distribution, and that's what we get, 0.129, and if I round to the thousandth here, I'm just going to get 0.129, okay, so here we go, so 0.129. All right, guys, I hope that was helpful for you and that you can complete your assignment based on this.